All right, so welcome back. Week 2 now of Physics 325, Optics. And last week, if we recall, what we did is we looked at Maxwell's equations and how they predict electromagnetic waves. And we looked at a particular form of the electromagnetic wave, the plane wave. And from that, we got some great stuff already. We found that there's this picture of light for these plane waves that it propagates along a given direction, okay? It propagates along a given direction, and the light is oscillating in a plane perpendicular to that direction. So light is transverse, and it can move in a constant plane where that plane represents a constant phase of the electric field. Furthermore, the electric and magnetic fields are related. The ratio of the electric to magnetic field is c, the speed of light. We also found out that light travels at the speed c. And finally, that these fields are in phase. So we already know quite a lot about light just from playing with the equations. We're going to look at a final physical concept of the light today, namely that it can transport energy. Okay, so light is an electromagnetic field. An electric field has an energy per unit volume, we're going to find out. And since it's a traveling wave, it is transporting energy. So another way of thinking about light, like this laser pointer here, is it's actually beaming energy through space at the speed of light. So let's get started in understanding that. The first thing we need to think about is the actual energy density of just static electric fields. Now it's a density, all right? So a plane wave is the same, it's constant everywhere. So what we really care about is the amount of energy in a given volume of space. Every cubic centimeter, for example, where there's an electric field, has some energy associated with it. Why? Well, that's potential energy, for example, that we can use to accelerate a charge and give it momentum, and kinetic energy. And of course, you always have to have copy of Griffith's electrodynamics handy. So if we look up the energy of these fields here, we can find that there's an expression for the energy, which you can calculate with some involved calculations in electrodynamics. But that's a different course for you guys. So we're just going to state the result today. If I look at the energy density, this energy per unit volume, we can write expressions for the electric and the magnetic field. By the way, we're using U for energy because it would get super confusing using E, because we're already using E for the electric field. So the electric, we're going to call this U, this energy per unit volume for the electric field. It turns out that it's 1/2 times the permittivity of free space, this epsilon, times the magnitude of the electric field squared. All right, so take the magnitude of the electric field in volts per meter, square it, times it by this constant epsilon naught. 1/2 of that is the energy I get in joules per cubic centimeter. Quite neat. By the way, there's a neat little derivation of this. If you just charge up a capacitor and look at how much energy it's stored, 1/2 CV squared. And you also know the electric field there, because it's not too hard to calculate a constant electric field between these plates. You can compare the expressions and derive this formula. Okay, so that's the electric, the energy density of the electric field. The magnetic field has a comparable density, okay? So that's 1/2 times 1 over permeability of free space, this is the magnetic analog to the permittivity, times the magnitude of the magnetic field squared, all right? So these are the two expressions. By the way, if you want another cute derivation of this, well, we just take the analog to our capacitor in electronics, a solenoid that creates a roughly constant magnetic field through it. We look at how much energy it takes to build up that magnetic field, equate them, and we can get this expression. Again, we'll just skip over those derivations now, but it's kind of a fun exercise that you can do. So no more solenoids or capacitors. But we see here that in a static field, E and B have associated energies for every cubic centimeter, cubic millimeter, or cubic whatever of volume, okay? So we're going to go a bit further. Let's look at dynamic fields now. Let's just look at our favorite picture for the course and of our plane wave propagating. And we have our electric and our magnetic fields here. And we can see that it's moving. So let's fix a spot, say right where those arrows are going. We'll just freeze space there and look at the energy as a function of time. Well, it'll look something like this, right? It'll have an electric field component and a magnetic field component, and they're going to be moving up and down in time. Notice though that because these fields are in phase, they're both going to be 0 at the same time, and they're going to be maximum at the same time, right? So that's kind of a neat fact, that because they're in phase, we can just add them up. The total energy density we get just from adding them up. We can go further. We're going to use the fact from last lecture that, remember this fact that the magnetic field, the strength of the magnetic field was the electric field divided by C, right? This is the fact that we got last time. And let's just square everything. Furthermore, we can use these numbers. These are special numbers in optics, right? Because we found that C is equal to 1 over the square root of epsilon naught mu naught. That's what the speed of light was. So that 1 over C squared is equal to epsilon naught times mu naught. All right? So let's use these three facts here and apply those to the the magnetic energy density. So here we're going to have 1/2 1 over mu naught, and B here is going to be 1 over C squared times E, so that's epsilon naught mu times E squared. These mu's are going to cancel, and this is equal to 1/2 epsilon naught E squared, which is the same thing as the energy density for the electric field. The magnetic field in a plane wave, or in light in general, the magnetic field and the electric field carry equal energy. The energy that it carries is shared equally between the magnetic and electric fields. All right, so that's kind of a beautiful result. In terms of energy, the electric and the magnetic fields are the same. And therefore, since they each carry half of it, we can talk about the electromagnetic energy density. The electromagnetic field has an energy per unit volume, and that's just going to be mu E plus mu B, since they're each equal and a half of the total. That's going to be epsilon naught times E squared. All right, and so if we plot these two fields over time, it's just going to be double. So the electromagnetic field density is given by this expression here. And for our wave, or a plane wave, we can write a form of the electromagnetic field. So it's this cosine, and that's what's plotted here. Okay, but remember, this is a traveling field. Okay, so we've kind of simplified things, and this week we're going to work to simplify them more to deal with rays and things like that. But remember what a ray actually is and what a plane wave actually is. It is a k vector, which is a given direction, and everywhere perpendicular to that k vector, we have the same field, right? So when I write a peak, a maximum here, that means everywhere in a plane perpendicular to this k vector here, we have the same amount of energy, and then it goes to 0. And then it goes high again, right? And this is being transported this way. So let's take a given area, a little square, or maybe my eye, and we ask how much energy is flowing into that area per unit time. All right, so here's an animation of a plane wave going through a square here, an area here. And there's a given amount of energy per unit time, or that is flowing through that surface, okay? So really what we care about is the energy per unit time per unit area. Okay, so let's get a handle on that. We're going to do a bit of math here. Okay, so we'll go to we'll look at what this actually means: the energy flow, the energy per unit time per unit area. Now, first of all, we'll clear up some space here. What is the energy per unit time per unit area? Well, the energy per unit time, that is called the power, right? Joules per second, watts, is energy per unit time. Power, and what we're interested in is the energy per time per area. So we want the energy per time per area. Energy per time per area is going to be equal to the power per area. And that is, well, it's the energy, the electromagnetic energy per volume, times whatever volume we're talking about, divided by some time interval times my area. So let's try to get a handle on this. So my area, what is my volume here? Remember, I had that little surface. I had that little surface that the plane waves are flowing through. And in a given amount of time, let's just fix delta t and let it be very small. What's going to happen is energy is going to flow through that surface, right, at the speed of light. It's going to go c times delta t. That's going to be the length of this little rectangular solid here. It's going to have a given area as well. So the volume is going to be whatever that area is times c times delta t. That's just the volume of this thing. So let's plug that in. So we have our electromagnetic energy density times the volume, which is A times C times delta T. And in the denominator here, we had delta t times A. So these areas are going to cross out. The time cancels out. And really, the power per area is just the electromagnetic energy density times C. Okay, kind of a neat result. The amount of energy in a given volume times the speed that it's propagating. So we can go a bit further. We can actually write that out. So that's going to be equal to, what do we say it was? Epsilon C times the electric field all squared. So that's going to be my power per area is going to be epsilon naught C times E squared, right? It's a scalar function, a number. But it also has a direction, right? The power is actually going in a given direction. It's going in the direction k hat. So we're going to call this thing here, we're going to call it the magnitude of some vector, right? This is just a scalar. A magnitude of some vector whose magnitude is equal to the power per area, okay? What about the direction? The direction of this vector that talks about how much power is going per area is k hat, okay? Now in principle, we can just do this. We could go S is equal to epsilon naught C times E squared times k hat. But there's a nice little way of writing this that encapsulates everything. It's kind of just a pretty way of wrapping up everything together, but it's also useful in terms of derivations. So we're gonna take this a bit further, and we're gonna actually talk about the direction that this energy flow is going. So note the direction of K is given by E cross B. This has to do with the fact that E is perpendicular to B is perpendicular to K. All right, so and given the right-hand rule, if I have E and B, well, K is going to be moving right out of your screen. So if the direction of K is E cross B, and that is the direction of energy flow, we can write this, E cross B. Remember the magnitude of E cross B. This is a fact from linear algebra, I guess. I don't know where you learn this. Is math somewhere. E times B times sine of the angle between them. And if these two things are perpendicular, sine, that's equal to 1. Sine of 90 degrees is equal to 1. So that's equal to just the magnitude of E times B. Good. Let's do one more thing here. B is equal to E over C. Or rather, I guess we can just write E is equal to C times B. Okay? So the magnitude of E squared is equal to the magnitude of C times E cross B. Okay, so this is just some mathematical gymnastics. We're saying that this is equal to 1 over C times E squared. Okay? So C times E cross B has the same magnitude as E squared. All right, so let's do one last thing here for these mental gymnastics. So it seems a bit convoluted, but it will give us a very nice result. We're going to multiply both sides by epsilon naught times C times epsilon naught C. And we have this vector here is epsilon naught times C squared now, E cross B. And that is called the pointing vector. Named after someone, but it also points in the direction of energy flow. So S, this pointing vector, has the same magnitude as we discussed before, this epsilon naught C magnitude of E squared, which we just wiggled our way to find that that's the same magnitude as epsilon C squared times E cross B, and it has the same direction as E cross B. So we can just wrap the whole thing up into this nice vector, this pointing vector, as it's called, which gives us exactly the direction and magnitude of the flow of light. Okay, so that is what we call the pointing vector. All right, so let's look what this would look like. Imagine if we're shining on a given area, the pupil, say, of my eye. So this would look like this, as this light is coming in. Energy is flowing into it as I'm looking at something, as I'm looking at the light from what's behind the camera here. Energy is flowing into my eye, and it's happening on some time scale, but it's pulsing on and off, right? So the magnitude of the pointing vector, sometimes 0, then big, then 0, then big, and it's oscillating like this. All right? How fast is it oscillating? The answer is very. Okay? It's oscillating very, very fast. So we have our pointing vector here. The magnitude of it is oscillating. How fast? Well, let's take red light. I might as well use a red pen for that. Lambda is equal to 600 nanometers. We also know that lambda times the frequency is equal to c. It's just for any wave. The wavelength times the frequency of the waving is the speed of that wave. So that the frequency is equal to, well, let's just look at it, c over lambda, which is 3 times 10 to the 8th meters per second, divided by 600 nanometers, which is 6 times 10 to the minus 7 meters. This is 1/2 times 10 to the 15 hertz. That's a lot of hertz. And if we flip it over, 1 over f is the time that it takes to pulse. In fact, it's the time that it takes for it to go maximum to minimum to maximum. So the energy, which is the square, is actually going twice as fast. And that's, just for the wave itself, is equal to 2 times 10 to the minus 15 seconds, 2 femtoseconds. And as I said, since it's pulsing, whether it's in positive or a negative, it's actually going to be 1 femtosecond to go pulse to pulse in this case. But it doesn't really matter. It just matters that it's very, very fast. So what we really care about is a time-averaged pointing vector. Okay, why? Well, let's look at that. A typical process, a chemical reaction, or the change of an electron orbital, is on the order of maybe picoseconds, but more like nanoseconds. Okay, the optical period, as we just found, is a millionth of a nanosecond, roughly. So a femtosecond is just like a flicker of time. Putting it conversely, a typical process, even very fast processes in nature, happen over many, 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 many optical cycles, millions of pulses of this light, right? So we typically don't see processes in nature, energy processes, where the transfer of energy happens cycle to cycle in the electric field. It takes many, many cycles, sometimes millions of cycles, for that energy to get transferred from one system to another. Okay? So what we actually care about often is the time-averaged pointing vector. Now it's not going to be 0, right? Because it's always positive. So if this is the max, we'll just call this 1 for now, and this is 0. The time average, roughly, I mean, we can kind of intuitively think that, should be about halfway, right? We kind of get two pictures here. We got waving this way. The whole area is this. The whole area is this rectangle here, and half the area is going to be roughly the average. Very hand-wavy derivation. Let's do it more mathematically now. But effectively, it's not going to be 0. It should be about half of the maximum value. This is the same kind of calculation you do when you calculate the RMS power in electronics. So let's look at the time-averaged pointing vector. So we're going to look at the time, let's just write that down. Time-averaged magnitude of the pointing vector. That's what we care about. That's how much actual energy we get on average. Well, if I time-average something, how do I time-average something? I divide it by the period, and I integrate that function from 0 to t. And in this case, what is the function? Well, it's just going to be the magnitude of s of t, dt. That's by definition the average over some period. And we're going to take the limit that averaging time goes to infinity of this average pointing vector. And we're going to give that a name, I. So that's going to be the intensity. The intensity is the limit of the average pointing vector as the averaging time goes to infinity. Okay, so let's dig into that a touch. So let's calculate this now. So we have 1 over t times epsilon naught, I'll use this form, c times e squared times the average of this cosine squared of kz minus omega t. Let's just call k equals 0. It's not going to affect the average, the starting point, of minus omega t dt. Cosine of minus omega t is the same as cosine of omega t, but forget about that. We'll just leave it in there. And we need to calculate this integral. All right, we'll use one of our favorite trig identities, the fact that cosine squared of x is equal to 1/2 1 plus cosine of 2x, right? There's that old formula. So if we plug that in, we're going to get 1 over t times epsilon naught c e naught squared times the integral from 0 to t of 1 times dt plus the second term, which is going to be the integral from 0 to t of cosine 2 omega t dt. Okay? So that's my second term here. This gives me a t, all right? And this term we have to calculate. So this is going to be epsilon naught times c, might as well leave the magnitude on there for generality, doesn't really matter. I'll be consistent, I guess. And that's going to give us t over t, so that's going to be 1 plus, what's this guy? Well, the integral of a cosine of 2 omega cosine is 1 over 2 omega sine, and evaluated at the bounds of integration is 2 omega times the period divided by, we have to divide this by 2 omega. And remember, we brought that t in there too. This is what it is. This is the average pointing vector as a function of time. Notice that this sine term, this is a sine x over x thing. The sine term is going to be bounded between -1 and 1. But t is just linear. This t here is just linearly increasing. It's in the denominator, so it's going to bound this term as 1 over t. So as t gets larger and larger and larger, this term is going to vanish, and eventually it's just not going to be there. And I forgot something. I forgot to put a 2 here. I apologize for that. So we got a 1/2 here. I'm sorry. This identity, this 2, escaped me the first time I did that. Okay, so we got 1/2 this. We're going to have 1/2 epsilon naught c times e squared times 1 plus this term, which vanishes. So for very, very short times, over a few cycles, this term is going to be significant, right? And then eventually it's going to die down. So this is epsilon naught c times e squared, the peak value. On average, we think it's going to be about half that value. And then we have this term, which, remember that sine x over x, and the limit as x goes to 0 is 1. So that's originally going to add a half, and then it's going to go down, and then it's going to go up, and it's eventually going to settle. All right? So if we actually did this, I calculated this in Python, and let's just animate increasing this for various times. So this is averaging for over a few cycles. And we see that it very quickly oscillates about a half of epsilon naught c times e squared. All right? So it turns out that although the definition of intensity is the limit as t goes to infinity, here infinity means like 10 femtoseconds or something like that. After like 100 femtoseconds or a picosecond, that's like an eternity. It's going to be negligibly different from 1/2 epsilon naught t squared. And that's still 1,000 times faster than the fastest kind of energy transfer processes that we typically see. So we can basically not worry about this limiting process, and we just define the intensity often as 1/2 epsilon naught times c times the magnitude of the electric field squared. Ignore that. I don't know if I'm blocking it. There should be a c there in front of there, like there is here. So I'm just going to write it up here as the intensity. For all intents and purposes, can be defined as 1/2 epsilon naught c times the magnitude of the electric field squared. Okay? And that's intensity. That's the power per unit area. All right. One last topic today. We've talked about how power is transferred. So now we're actually going to talk about how another interesting fact is that imagine we're shooting this laser pointer here, and it's giving out an electric field. There's an energy that's being transported through space. Let's hit something like this this screen here, this black screen that has a keynote presentation on it right now. Basically, if the light gets absorbed, there is a given amount of energy flowing this way at one instant, and then at another instant there was no energy, there was no light behind there, and there's an energy transfer. It's gonna, in fact, if I could zoom in to, I don't know, probably picometers, I'd see that this thing actually gets pushed back a bit, right? The screen gets pushed back a bit by virtue of the energy transfer gets stopped there. We can think of that as a pressure. And indeed, there is a measurable radiation pressure. This is something real that you can actually measure. And you actually have to worry about it either when you have ultra intense lasers, so you can actually utilize it for ultra intense lasers, or when you're doing things like shooting photons at individual atoms, and you have to worry about the recoil. Okay, so we're going to talk about it classically first, and then maybe we'll mention it quantum mechanically a bit later when we talk about photons. So classically, how do we think about this fact that light is traveling at a speed and transferring energy? Okay, so if I had a laser pointer out in space, there'd be some reaction force, or if I pushed on an atom, that atom would get accelerated from this radiation pressure. Let's think about that. So the intensity, hey, we have it written here. That's power per area. Well, let's just keep going with that then. The power per area is the energy per time, not the energy density, but the energy, the total energy per time. That's the power per area. Okay, and again, I'm pushing these photons, or the electromagnetic field is just displacing this as that pressure gets built up and is transferred to a surface. Even though it's going to be very, very minute, that transfer of energy means that it's going to move a bit. So we can think of that as some displacement. And if you remember way back in first year, force times there's the work energy theorem. Force times x, F dx is equal to the work, and that's equal to the energy transferred. So force times delta x is what we're going to use for energy. Okay, and that's going to be A times delta t. But look here, if I just break that line here, I have force per area. That's a pressure. I already have a P here, so I'm going to give it a curly P. PR. That'd be radiation pressure. Radiation pressure. I'm under pressure to spell properly. Times this, which is C. In other words, the radiation pressure, the pressure, the physical force that the sheet is feeling per unit area, is given by the intensity divided by the speed of light. Okay, and that's written up here. So the radiation pressure is the intensity divided by the speed of light. You can calculate it. It's not going to be much. So an intensity might be what's a good intensity? A kilowatt per meter squared, or something like that. Okay, so that's 1,000 divided by speed of light, 10 to the 8. So it's going to be on the order of 10 to the minus 5 newtons per meter. That's something like an ant. The difference between an ant being on a meter squared desk or not. That's a tiny, tiny pressure. But if you have a large enough laser and a light enough object, there's real consequences. In fact, there's a very crazy project right now called Breakthrough Starshot by some Silicon Valley millionaire and entrepreneur who wants to send a probe to our nearest stellar system, Alpha Centauri. So there's a number of ways you can do this, but it just turns out it's very, very hard to accelerate things to fast speeds. And you want it to be fast. So if you just want to go for a classical, I don't know, Gemini or satellite going through our solar system now, that technology, well, we'd have to wait, a few tens of thousands of years for it to get there. And we kind of want to see it in our lifetime. So in order to accelerate it to speed at which we can see it in our lifetime and cover those 4 point whatever light years, we need to be moving at a considerable fraction of the speed of light. And it turns out kind of the only technologically feasible way that these people found to do it is to use radiation pressure. Okay, so we'll get some very, very big, terawatt array of lasers, and we're going to shoot it at a solar sail that's in space. A solar sail is made of a very, very light reflective material. Maybe it's a couple meters by a couple meters, and it weighs like a gram. It's a very neat material science, and it'll have like a little chip on it to translate. And these lasers are going to be focused as well as you can. There's a limit to this, to hit this laser. Shine at it, hit it for a few minutes, and it turns out that if you have a sufficiently powerful laser, you can accelerate it. There's a cartoon of it, I guess, or an illustration of it. It's called Breakthrough Starshot. And I think the idea is that within a few minutes, it will have gone like several times the distance to the moon, and we can shine the light on it for a given amount of time so that it reaches something like 0.2 C. And so it's going 0.2 C. That means it would take about 20 years to get there, another 4 years for the signal to get back, and maybe we could snap a picture, if this thing works, of our nearest stellar system and solar system, I guess. So this is great. So this is a real thing that's really being used in engineering. to make these crazy devices. It's also very important in things like optical tweezers and laser cooling when you worry about the recoil of very light things. Okay, that's it for today. Let's summarize. The fact that electromagnetic fields, electric and magnetic fields, have energy density associated with it, and we combine that with the fact that it's traveling at the speed of light, means that we're transferring energy, that light is beaming energy. A laser is literally beaming energy through space at the speed of light. So we can actually quantify that with this so-called pointing vector, which is epsilon naught times c squared times E cross B. And that the time averaged pointing vector is what we call the intensity, 1/2 epsilon naught c E squared. Finally, another consequence of this light, of energy being transported by light, is that we have radiation pressure. Physical pressure can be exerted on an object, and the magnitude of that is given by the intensity divided by the speed of light. So next time, we've kind of talked about all the physical properties of light in free space. And now we're going to simplify things in the next video so that we can start talking about rays and making images and doing more sophisticated things when light interacts with matter. And we'll see you then.